Hello all, welcome back. I wanted to start into our second part of Chapter 5. Now that we understand our concept of the mole, we're going to look at how moles apply to solutions. In a lot of cases when we're trying a chemical reaction, when we're doing a chemical reaction, we will put the chemicals into a container like a beaker or a test tube or a flask, and I will take my one chemical and add it to my second chemical. But it turns out if they're solids, the only part of those chemicals that can react with the other chemicals are the surface of the chunks. So if they're crystals, the only part of that crystal that can react is the surface of the crystal. And it turns out, if you could imagine, say, me, and you look at the surface of me, which would be my skin, you say, okay, well, if Mr. Senna weighs, say, 200 pounds, and let's say if I could take all of his skin off and weigh his skin, which is the surface, which is on the outside, maybe it weighs, 5 pounds. That means there's 195 pounds of me that can't react with the outside world because it's being protected by my skin. It's being covered by my skin. And the same thing happens with solids. So in a lot of cases, in order for a chemical reaction to happen in a way so that all of the chemical can react, we dissolve it. Right? We dissolve it often in water. Water is probably the most common solvent, and we'd make something called a solution. Now, when I dissolve something in a solution, the crystal disappears. So think about salt in water or sugar in water. And when it disappears, that chemical basically fills, it separates. Every NaCl, every sodium chloride separates from every other sodium chloride, and they're all floating around in that water now, ready to react with whatever I'm putting in there. Maybe it's, say, silver nitrate. Right? So if I was to look at, let's just say, a reaction between silver nitrate and sodium chloride, trying a new stylus here. And my products, oh goodness, my products would be silver chloride and sodium nitrate. Okay, so there's the chemical reaction that I'm looking to happen. Now, if I've got a chunk of NaCl and a chunk of AgNO3, the only part that can react is the solid. But as soon as I dissolve them in water, now all of the chemical is floating around freely in the solution. So solutions become a really important part of chemistry. And almost all the chemical reactions that I can think of, every reaction that I do in grade 11 chemistry, in grade 10 chemistry in science, in the chemistry unit, in grade 12 university or college chemistry, the chemicals are suspended in water. They're dissolved in water. Water becomes not anything that has to do with the reaction itself. All the water is doing is separating the molecules so that they can now react with the other reactant. Right? One chemical can react with the other chemical. So there's the idea here, is I need to make a solution. I need to dissolve something so that I can maximize the amount of reaction that happens. So we're going to talk about this word solution, and a solution is a mixture of two or more pure substances. Now, the pure substances are whatever is, let's say, if I put salt in water, the water becomes the solvent. It's the thing that's going to be doing the dissolving, and the salt would be the solute. It's the thing that's going to dissolve, right? So I've got this solvent, and I've got the solute. Those are the two pure substances, right? Again, for the first one, maybe the solvent is H2O, and the solute is sodium. I'm gonna have to switch is sodium chloride. Okay, so those are my two chemicals, water and sodium chloride, and they're both pure substances. Okay, and the solvent is the one that's going to be doing the dissolving, like the water. It's the one that's going to dissolve the other one. And the thing that dissolves is called the solute. So I could take sugar and dissolve it in water. Water is the solvent, sugar is the solute. I can take a liquid in some cases. The liquid might be, let's say, what would be a good liquid to look at? Let's say I'm talking about ammonia, right? If we're making a cleaner. And ammonia is a pure substance, NH3, nitrogen trihydride, and I'm going to add it to water. And even though it's not really dissolving, it is spreading out. It is being separated from itself in the solvent, right? So water would be the solvent, and the ammonia, the NH3, would be the solute. So those are the two parts of any solution. Now, we know, let's say if you're a coffee drinker, you know that when you're ordering a coffee, you may order a coffee with a certain amount of sugar. Or maybe you order it with a lot of sugar or a little bit of sugar. Let's say one sugar in your coffee, or a double or a triple. What we're talking about is how much solute, the sugar, is going to dissolve in your solvent, which is the water, which is going to be basically your coffee. Coffee is 99% water. Right? Now, if that's the case, I've now made a solution. Something is dissolved in something else. If I've got an aquarium at home and it has a salt water aquarium, right? I need to every month or every 3 weeks, whatever it is, I don't know exactly, take some of the water out and add more salt water to make sure that the concentration of salt and water works for my tank. So to make the salt water solution, I need to dissolve my solute in the solvent. If I have a tea bag, right, and I take my tea bag and I put it into water, the chemicals that are in the tea bag, which are called solutes, will dissolve in the water, and I will ultimately make a solution which is called tea. Right? If I look at a swimming pool, if I take chlorine and add a liter or 2 or 4 liters of liquid chlorine to a swimming pool, the chlorine is the solute, and the water in the pool is the solvent. Usually there's way more of the solvent and just a small amount of the solute. Again, think about the coffee again. You got a teaspoon of coffee in a cup or a cup and a half of hot water or hot coffee. Again, a solvent doesn't necessarily need to be a liquid. I would say 99% of the time when I think of a solvent, I think about water. But it's possible, if I think about how a breathalyzer test works, a breathalyzer tells me how much alcohol is dissolved in my breath. So if I get pulled over on my way home from wherever I am in December, and there's a Christmas ride program going on, and the cop says, roll down your window, breathe into this thing, right? And what he's doing is he's measuring the concentration, how much solute is in my solvent, right? Which is my breath. And I don't drink, so it should be 0. But if we are talking about different people after maybe coming home from a party at Christmas time, perhaps they might have more solute in their solvent, more alcohol in their breath. And if it's above a certain concentration or a certain level, then we know that it's probably going to impair that person's ability to drive the car effectively. We also talk, again, if you've got asthma, one of the things you might sometimes look at is how much solute here. The solute would be air pollutants that is in the solvent, which is air. You think pollutants aren't dissolved in air. Well, basically they are dissolved in air, right? I've taken a certain concentrated chemical and I've spread it out, right? And that's basically all we're doing when we're dissolving something. And then ultimately it gives us a number. The number is called the air quality index, and the air quality index tells me how much of the solute is in the solvent, how much pollution is in the air today. And they might say to you, if you have asthma, you just want to stay home today because there is too much pollution in the air, and it's really going to bug your asthma. You're going to have a hard time breathing. Now, the operative word here for today is the word, is the word concentration. Concentration tells me how much solute is dissolved in the solvent, right? How much solute. So if I've got, again, think about coffee. If I take my coffee black with no sugar, the concentration of sugar is 0, right? It's how much solute sugar is in my coffee. If I have 1 spoon of sugar, it's got a certain concentration, right? That's tells me 1 spoon per coffee. If I increase my concentration, maybe I put 2 spoons of sugar, it's a more concentrated solution. So when we use that word concentration, concentration is talking about how much solute is dissolved. So we sometimes talk about the word concentrated. If I say it's a concentrated solution of something, that means it's a very strong solution. There's a lot of solute dissolved in that solution. A solution that has a very low concentration we often call a dilute solution. Right? A dilute solution is going to be what I might call a weak solution or not a very strong solution, and I would say that it has a low concentration. Right? So concentration is telling me how much solute is present within my solution. Now there's different ways to talk about solutes. Okay, one of them is by using something called a percent composition. And just like we would, again, know what a 78% means on a test, or a 52%, or a 98%, or a 36%, we can do the same thing with concentrations of solutions. How much of the mixture is the solute? And in a lot of cases, they're going to be very small numbers. Now, there's 2 ways to talk about a percent concentration, and it depends on whether or not the solute is a solid or a liquid. If the solute is a liquid, again, think about pouring liquid ammonia into water. Right? If I take 1 milliliter of ammonia and pour it into 99 milliliters of water, I now have 100 milliliters. And to find the concentration, it's going to be the 1 milliliter divided by 100 milliliters, so 1 out of 100. Again, think about that on a test. It means you got 1% on the test, right? 1 divided by 100 is 0.01 times the 100 here, and that would give me a concentration of 1%. Okay, just like we would on a test. If I've got, say, 4% milk, right, or 2% milk, right? 2% milk means that in 100 milliliters of milk, there are 2 milliliters of basically fat. Okay, so I've got 2 milliliters divided by 100 milliliters of milk, right, times 100%, 100, and I would get 2% milk. Right, so that's one way to talk about a concentration. And that's usually when we've got a liquid dissolved in another liquid. Now, the unit will be a percent, right? Because it's basically going to tell me how much of that solution is that particular chemical. If I look at some other chemicals, we often talk about a different type of concentration, where that one was called volume per volume, or V over V concentration. This one is called mass over volume concentration. And for a mass per volume concentration, you probably can imagine it's going to be the mass. In other words, how much, I'm going to weigh it, how many grams are there in 100 milliliters of solution. Right, so if I've got 1 gram in 100 milliliters, it's a 1% solution. If I've got 10 grams in 100 milliliters, 10 out of 100, right, that's 10%. I've got a 10% solution. So when you go and you get, if you're in the, say you get sick and you go to Emerge and they put one of those IVs into your arm and it's dripping that big bag of saline into your arm, that's 0.9% sodium chloride. That means if I took 100 milliliters of that liquid, 0.9 grams of sodium chloride of salt is dissolved in that 100 milliliters. Now, there's way more in it than that, but that's basically the ingredient that they're probably trying to top you up with. So I'm going to be taking the mass of solute now, how many grams, and divide it by the volume of the solution in milliliters, okay, and then it will give me a percent. So if I've got, let's say, 35 grams of sodium chloride, so I'm going to get my scale out, I'm going to weigh it like a kitchen scale, and I'm going to dissolve it in 1 liter of liquid. I'm going to make it up to 1 liter by adding the 35 grams to water, and then keep adding water till I get to exactly 1 liter. Okay, that becomes concentration is mass of solute divided by volume of solution. The volume must be in milliliters and the mass must be in grams. So to do this, I'm going to take my mass in grams, 35 grams of sodium chloride. I'm going to divide it by my 1,000 milliliters or liter of final solution, and that gives me a final concentration of 3.5%. Now notice that when we do this, we also report not just the percent itself, but also the fact that it's a mass per volume percent. 3.5 grams in 100 milliliters, or 35 grams in a liter. If I look at the one that I had up here, this was a volume by volume percent. Right? Volume by volume, that means 5 milliliters in 100 milliliters. So where the first one up here was looking at having a liquid in a liquid, this percent down here is when I've got a mass, a solid, dissolved in a liquid. Okay, now, that being said, that's helpful for some things that we do, but for the most part as a chemist, right? Remember, we're talking about how many atoms or how many molecules, or in this case, how many moles of a chemical are dissolved in a liter, right? This becomes the one that chemists use. This is called the molar concentration, right? This is the one that I always use and that you will always use. Those percent calculations, percent concentrations, they have specific uses like air quality index and alcohol, doing a breathalyzer test. They have their own uses, but for the most part for a chemist, I care about how many molecules or atoms are present. But again, an atom or a molecule is too small. We talk about moles of atoms. So when we're talking about molar concentration, our concentrations are how many moles are in a liter, right? And to do that kind of work, I need to be able to calculate the number of moles in a liter by taking the number of moles, N, again, little n is number of moles that we've been using for the last week, divided by the volume, which is measured in liters now. And then what I end up with is a concentration in moles per liter. Okay, moles per liter. So all I've done is I've taken the number of moles, divided it by the number of liters, and I end up with a unit that is in moles per liter. Okay, so I'm going to switch to page 188 and look at the sample problem that they've given you in the textbook, and then there's a few for you to try. Okay, so let's go back to my scratch pad here, and I'm going to do the sample. It is sample number 7, and it's on page 188 of our textbook. And it says a 100 milliliter solution of IV solution, oh, that's the stuff that they're going to drip into your arm, contains 5.10 grams of glucose. What is the molar concentration of this solution? Okay, so what am I given? I'm given the volume, which is 100 milliliters, 100.0 milliliters actually. Now remember, I need to have my volume in liters. So I'm going to convert this. I know that 1 liter is the same as 1,000 milliliters. And my milliliters in the numerator here and in the denominator cancel out. And now I'm going to take my 100 from here, divide it by my 1,000 down here, and I'll end up with 0.1000 liters. Remember, I've kept all those zeros there because they are significant. We talked significant digits. Those zeros are significant. I'm also given the fact that there is 5.10 grams of the chemical glucose, which is going to be dissolved in that 100 milliliters. And we're told that glucose is C6H12O6. And it gives me one more piece of information in the question, and it won't usually, but it does for this question. It says the molar mass for glucose is 180.18 grams per mole. Molar mass. That's capital M. Again, from all the work we've been doing this week, and it's 180.18 grams per mole. And my required to find here is the concentration. Concentration is always in moles per liter. Okay, so to calculate my concentration, C equals N over V. N is the number of moles, V is the volume in liters. This formula here is actually on your periodic table at the bottom of the page, so again, you don't need to memorize this one. Just like the first two that we've used, the little n equals mass, little m divided by big M, and little n is also equal to big N, number of particles, divided by Avogadro's number. Those two formulas that we've been using are also at the bottom of your periodic table. So now if I want to go ahead and start doing some of the math, okay, I need to know N and V. Well, I know V. V's up here. Okay, my volume is given, but I don't know N yet. So I'm going to have to find N. I'm given a mass, and a molar mass. So I can actually solve for N. Number of moles is mass divided by big M, molar mass. Right, that's again on your periodic table. If I do the math, I'm just going to work across the page here, is 5.10 grams divided by 180.18 grams per mole. And I'm getting a number of moles, which is 0.0283 moles. Notice I've kept 3 digits in my answer here, 283, because I had 3 significant digits, 5.10 up there. Now again, I'm not going to be very finicky about or fussy about my numbers of moles, of significant digits, but just to be aware that we really should be following through with this all the way through. So I now know my number of moles, I know my volume, I know N and I know V, so I can now solve for C. So let's go ahead and substitute our numbers in now. So let's solve by saying C equals N over V. N is 0.0283 moles divided by V, which we said was 0.1000 liters. And my C turns out to be 0.283 moles per liter. Okay, so if you go to the hospital and they have the drip going into your arm, the concentration of sugar, if it's a glucose drip, the concentration of sugar will be 0.283 moles per liter. So phrase, therefore, the solution is 0.283 moles per liter of glucose, which is the chemical which is dissolved in the solution. All right, so Again, maybe the trick to this whole thing, or part of the trick, is going to be keeping our letters straight, right? What are our letters? Let me just scroll this up a little bit here. Okay, so I know that little n is the number of moles. Let's say big N, which was the number of particles. We've got little m, which is the mass in grams. Moles is M-O-L. Big M is molar mass. That's in grams per mole. And now we have C, which is concentration. In other words, how much chemical is dissolved in my solvent. And it's going to be in moles per liter of solution. Okay, so if I go back to my note here, so this is in 5B now, right, is where, 5B is where this next set of last three sections, 5.6, 5.7, and 5.8. So I'm going to stop there for now and leave you with these questions here on page 180.